A famous mathematician from several hundred years ago, whose name was Carl Gauss. You may have heard his name associated with something called a degausser, for example, which is a device for straightening things up electronically. There's a story that is supposed to be true about Gauss, but I suspect it's apocryphal. Apocryphal is a 50-cent word, which means it just isn't true. It's a cool story, though. One of his grade school teachers asked the class to add up the first 100 whole numbers from 1 through 100. Now, the way we write that without taking up our entire day writing all these numbers out is we put dot, dot, dot. And what that means is look at the previous numbers and see the pattern. So this means 1, 2, 3, all the way up to 100. Add those together. And Gauss, it has been conjectured by some people, worked this in a very clever way. He said, you know what, if I call that total A, and I wrote it backwards, starting with 100 and then 99, 98, 97, it's still going to add up to A. I hope that makes sense to everyone, because the order in which you add numbers doesn't make any difference. So what would happen if you added the top row of 100 numbers to the bottom row of 100 numbers? Well, you'd get A plus A, and that would be 2 A's. Now, notice each pair that are vertically above each other add up to 101. 99 plus 2, 98 plus 3, 97 plus 4, and so on, 100 plus 1. So these totals can be added that way, and it's going to be equal to 2A, and they're all going to be 101. And how many of them are there? Well, from 1 to 100 is pretty easy. There's 100 of them. So in this case, 2A is going to be 101 times 100, and that's not too hard to solve. Let's just go ahead and look at the calculation. It's, well, 101 times 100 divided by 2 is 5,050. Pretty easy way of adding up 100 numbers. Now, it turns out that this is good for other things as well. Let's see if I can find those other things. Maybe. Okay. Let's go ahead and take a gander at our little book, because I want to show you the pages that you need to know about. Well, here's one of them. It's on page 40. Page 40 is going to be huge, just like page 30 was huge in the last test. So this is called arithmetic series. It looks like the word arithmetic. They're spelled the same, but arithmetic is a noun and arithmetic is a verb, and English is really, really difficult. So when you have a bunch of numbers added together, it's called a series. If you just make a list of those numbers, it's called a sequence. So when you add up the sequence, you get a series. Now, sometimes you can actually determine the sum of a series when the individual terms, that's what they're called, first term, second term, third term, when the individual terms are related in a certain way. In this instance, you can see 3 plus 10 plus 17 plus 24, and again, plus, and so on, continue the pattern until you get to 346. So what is the pattern? Well, I'm pretty sure you can tell the pattern is add 7 to the previous number. Now the 3 can be any number at all, but then after 3, we add 7 to get 10, we add 7 to get 17, we add 7 to get 24, and hopefully, if they're not trying to trick us, we keep adding 7s until we land on 346. And the problem is, the challenge is to figure out what the total of this is without actually doing them one at a time on your calculator. But here's what you have to know about this. When the numbers in a series are related by the fact that every number in the series plus something gives you the next number. 3 plus 7 is 10, and the same something. 10 plus 7 is 17. 17 plus 7 is 24, and so on. And this is what makes it an arithmetic. So to figure out the sum of this arithmetic series, we need to know 4 numbers. And they are what I call the adder. Now, in the mathematical world, it's called the common difference. The difference between the first two terms is 7. The difference between the second two terms is 7. It's a common difference, and that's why we call it D. So we need to know the common difference, or the adder. We need to know the last term of the series and the first term of the series. And we also need to know how many terms there are. How many numbers are we adding? And that's going to turn out to be, in some cases, the most tedious part of it. So the first term is designated with a subscript, A sub 1, and that's 3. It's the first one on the left. The order makes a difference. Now, the last term I'm going to call A sub n is 346. Now, in higher math, they get real creative with these subscripts, they're called. This is not like an exponent. It just identifies this 3 would be A sub 1, 10 would be A sub 2, 17 would be A sub 3, and so on. And you don't have to start off with, well, you could call this one A sub 0 or A sub 12. It doesn't make any difference, but everything is going to be changed if you don't start with 1. All right, so it turns out that the number of terms, because we got to know how many terms there are, it can be calculated by either one of these two formulas. The number of terms, that's the number of numbers we're adding up here, is going to be the last term, A sub n, minus the first term, A sub 1, divided by that common difference, the adder, and then you add 1 to that. Now, there's a reason for that, and I would like to point out what that is with this example that we had with Gauss. Notice that the number 2 is 1 more than 1. This is not earth-shattering news to you, but 2 is the second term, and 3 is 2 more than 1. And 4 is 3 more than 1. And 6 is 5 more than 1. So when you get up to 100, how many more than 1 is 100? Not too hard. I think you figured that out already. 100 is 99 more than 1. So, but how many numbers are in this series? Well, if you just counted from 1 to 100 out loud, you would say 100 numbers. So there are 100 numbers in this series, but the last number in the series is the first number plus 99. It's not the first number plus 100. And that's going to be a little guidance for when we have a little issue with why did you do it this way? Okay, so it turns out just as we did for Gauss, that little story about Gauss. Whoops, wrong one, sorry. Okay. Let's suppose that we take a look at this guy again. And this, I think you will notice, is the same one that we have in the book, 3, 10, 17, 24, all the way up to 346. All right, well, we could do the same sort of thing we did before. We can call the sum A, and we can write it backwards. 346, and the one before that is 339. It's 7 less, and the one before that is 332, and all the way down to 3. And again, if we add the top row to the bottom row, we get A plus A, which is 2A. And if we add vertically, 3 and 346 is 349, 10 and 339 is 349, 17 and 332 is 349, and so on all the way out to 346 plus 3 is 349. And the reason that's so is, look, when you have A written from 3 higher, A goes up by 7 at every turn, and A down here goes down by 7. So in the first row, the second term is 7 plus the first term, and in the second row, the second term is the first number minus 7. So if you take 3 and you add 7, then you take 346 and you subtract 7, that's going to basically cancel out, and that's why every single pair of these vertically aligned, more or less, terms will add up to 349. So what? So the tricky part is we have to figure out how many numbers there are so that we can say 349 times something. But how do we do that? Well, here's how we do it. we take the last number, which is 346, we subtract 3, divide that by the adder, the common difference, and that's 343 divided by 7, and then we add 1. Now, why do we add 1? It's the same reason, because in this particular series, the 346, if that's the nth term, so the number of terms is n, then 346 is not going to be the first term plus n sevens. It's going to be the first term plus n minus 1 sevens, because the second term is the first term plus 1 7. And in general, like the fifth term is the first term plus 4 sevens. So the nth term is the first term plus n sevens. So what happens, n minus 1 sevens. So then this division has to come out even, because if it's the number of terms, it's got to be a whole number. You can't have minus 12 terms or 3.5 terms. So that's 49 plus 1, which is 50. And once we figured that out, now we can figure out what A is. That was the goal in the first place. What is 3 plus 10, blah, blah, blah. And we would simply, can I say simply, plug in the formula numbers, and there we have it. Oh, well, didn't finish that, I guess. So let's take out our little calculator and do 349 times 50, 349 times 50. And that's equal to that. Divide that by 2. And we get 8,725, which is the same thing we got over here on page 40. So page 40 gives you an example of how you calculate the sum of a geometric series when you're given a string of numbers like that, and you are told that that pattern continues, adding 7 continues until you get all the way up to 346. Okay. This is going to be a little weird. I remember going to college as a math major. The first time I saw this crazy thing that everybody thought was a giant letter E, but it's not. It's a capital letter sigma from the Greek alphabet. And sigma is used because, well, it means the sum, S-U-M, and sigma is S in Greek alphabet. And it's got these cool little horizontal bars that you can write stuff next to. And the way you read this is the sum from k equals 1 to 50 of 7k minus 4. That's how you read it. And this is what it means. I want to know what is the total of all the numbers that are calculated by replacing k with 1, 2, 3, 4, 5, all the way up to 50 and performing the operation. For example, 7 times 1 is 7, minus 4 is 3. That's where the 3 comes from. 7 times 2 is 14. 14 minus 4 is 10. 7 times 3 is 21. 21 minus 4 is 17, and so on. 7 times 50. See, we don't have to write all of them out. It would take too long. But we do have to know the last term. So we plug in 50 to get the last. Remember, the last term is not the same thing as the last number you plug in. The last number you plug in is 50. And when you do that, you get 7 times 50 is 350, minus 4 is 346. And that is how you get the last term without having to write out all 50 of them. Okay, this is the same one we've been talking about today a little bit already. In general, a series that looks like this, now this is going to be a little odd. This is a math class, but here's a little, well, it's an expression that doesn't have any numbers in it, just a bunch of letters. But in general, in a series of the form, the sum from k equals a to b, like k equals 1 to 50. So a would be 1 and 50 would be b, and then dk would, well, d would be 7, and then k would be k, same k as that, and plus c, well, this is a negative, so this would be dk, this would be 7k plus a negative 4, which is the same thing as 7k minus 4. So that's going to be an arithmetic series. And here is the really useful part of this. When you have sigma notation, and you have limits. The number on the bottom is the bottom limit, and the top is the upper limit, excuse me, and the lower limit. It turns out you can calculate the number of terms regardless of what goes in here to the right of that. It doesn't even have to be arithmetic. It could be anything you wanted. But if you're going to add up some numbers and your variable goes from 1 to 50, the number of numbers is going to be b minus a plus 1. Why plus 1? Well, because, for example, 50 minus 1 is 49, but there's 50 terms in here. You got to add 1. All right. Upper limit minus lower limit plus 1, or top minus bottom plus 1. Now, if the series is not given in sigma notation, we have to use one of the formulas on page 40. All right. Notice that the upper and lower limits can be any whole numbers. For example, the sum from 5 to 54 of 7k minus 32 would equal, it turns out, the same one we've had before, 7 times the first number we plug in. See, k isn't 1, but 5 is the first number we plug in. And we do 7 times 5 is 35, minus 32 is 3. And then plug in the next number, the next whole number larger than 5 is 6. So then it's 7 times 6 is 42, minus 32 is 10. And then we plug in 7. 7 times 7 is 49, minus 32 is 17. And if you notice carefully, this is the same thing we had before. We've had it twice now. This is the third time. So you don't have to write them all out, but write out enough to see what the pattern is. And the pattern is add 7, add 7, add 7. But we do have to plug in 54. We got to know what the last term is. So that's going to be 7 times 54, 7k minus 32. 7 times 54 is 378, minus 32 is equal to 346. So you can probably gather that there's an unlimited way of writing a sigma notation that gives the same series over and over again. We normally start with 0 or 1, but you don't have to. All right, and the number of terms I want to point out is not 49. It's 54 minus 5 plus 1. There's 50 terms, which we already figured out before. Now, alternatively, if you really want to do this and you don't want to use the handy dandy sigma notation fact that top minus bottom plus 1 is how many terms there are, you can use the formula from page 40, which is the last term minus the first term divided by the adder, the common difference, and then plus 1. And we've already done this, and you're going to get 50. So now, the other formula that we need is the formula from page 40. I believe it's page 40. We'll find out pretty quick. Yeah, the formula for the sum, I call it a sub n. That's pretty standard. The total of all those numbers is a sub 1 plus a sub n in parentheses times n. And what that means in words is 3, the first term is a sub 1, the last term is a sub n. So 3 plus 346 times 50 divided by 2 is 8725 again.